Morning, good morning, buongiorno. C'è qualcuno? Sì, 9. Mi sentite? Can you hear
Sì, la
me?
sentiamo.
Bene. Ok. Welcome to our last lecture on plasma waves. What we are going to see today is we are going to finish our derivation of the Alfvén speed for Alfvén waves, and then we'll briefly discuss about parametric instabilities, and if we have time, the laser rocket for inertial confinement fusion. So let's start setting up a timer for the first break. Let's take 40 minutes lecture, okay? And let's recap what we seen last time about Alfvén waves. So these waves are somehow different from what we did in the linear approximation. So we do not use the linear approximation anymore. We concentrate ourselves on MHD equations for the so-called ideal MHD, where there's no resistivity. So the B field is not diffusing, and the fluid and the magnetic field are moving together inside the plasma. So what is called the frozen in flow behavior. Then we want to look for transverse waves that are that have the oscillating variables. In our case, will be the magnetic field and the fluid velocity that are oscillating in a transverse direction with respect to the wave. The direction is given by the field lines of the magnetic field. And since we are in MHD, we are talking about an externally applied magnetic field that usually in our laboratory plasma is used to confine the plasma in a given region of space. So M0 is the externally applied field. And using the expansion in plane waves, it means that we will have planes of equal phase, equal values of the quantities progressing in the direction of the wave. And for this reason, the quantities are not dependent on the transverse coordinates. We are X and Y. If we decide to put our frame of reference with B, the magnetic field, along the Z axis. In that case, the oscillating and propagating quantities won't have any dependence on X and Y, so the nabla operator can be reduced to a very simple formula where we don't have the partial derivative with respect to X and Y. The only partial derivative that is acting is along the Z direction. So we focus ourselves onto a situation where we have incompressible fluid, and that means that this simplifies the momentum equation as we've seen for electrons. We don't have the convective term. It means that for the velocity, it means that the divergence of the velocity field or the fluid velocity is zero inside the plasma. In this case, then, we decided to distinguish between the external applied B field and the B that is arising from the phenomenon of the Alfvén wave, and which actually is propagating along the B field lines. And since it's not a perturbation anymore, it's going to be, can be very large in amplitude, we have to consider in the dynamical equation for the electrons not only the externally applied field, but the contribution of the B field of the wave solution as well. So the total magnetic field is the sum of two important terms that we have considered both. And these two terms are divided in terms of space into categories. One is the external applied field that is constant and is has only the Z component, whereas the wave solution, the B field of the wave, has only components in X and Y. So, and we've seen that actually using the constituent equation for the B field, so that the total magnetic field is solenoidal. This means that it's not changing, the component has not to be changed along the Z direction, and this means that actually we are considering a situation where the externally applied field is constant in space and time. Then we, when we apply the time derivative to the B field, obviously what enters this time derivative is only the component of the wave. But this, the time derivative of B dot is linked to the curl of the electric field in using the Faraday's law. Since we are in ideal MHD, we can actually write exactly the E field in terms of the current density J and B dot, since in ideal MHD we have a perfect balance in charge. So by using the Ohm's law for ideal MHD and re-expressing the E field and doing some maths about the vectors products, then we end up with one equation, one dynamical or evolution equation for the B part, the magnetic field part of the wave, that tell us there's the time derivative of this B magnetic field is proportional to the amplitude of the external applied field and to the gradient along the Z direction of the velocity field, the fluid velocity. Now we have to somehow couple the fluid velocity back to the magnetic field in order to initiate what is the wave phenomenon. So that one perturbation in B field produces a perturbation in the fluid velocity that in turn generate another perturbation in B field, and so the wave start propagating. Okay, so the equation that we need is the dynamical equation for the velocity field. This one here. So we go to the Newton's law for the fluid, and we have that the mass times the acceleration of the fluid is equal to the pressure forces acting on the fluid, so minus the gradient of the pressure of the fluid, plus the magnetic force, which is J cross P. And here's where we arrived last time. So we have to go ahead from here. So we start working on the magnetic force, which is composed of the current density and the total magnetic field. In order to compute this term, we use the Ampere's law to express what the current density J is inside the plasma, and we find out that we have to compute the curl of B vector product, the total magnetic field. So the first task was to compute the curl of B using the usual approach of the taking the determinants with the Cramer rule. So we have IJK, and for instance, let's recall what we did. The first component is this term here, so it's 0 minus dz dbj. So then the second term is going to be 0 minus dz bx, and we have to change the sign, so it becomes a plus dz bx, and then the third, the z component of this curl is just 0 times 0, so it remains 0. Now we have to compute the cross product of the first term against the total magnetic field. So let's do that in the next page. So today is the 14th of May, 2001, and we have to compute, let's write it again. So J cross B dot, where J is 1 over mu naught, the magnetic permittivity of vacuum, and then we computed the curl of B. So this is dz by minus dz bx 0, if I remember right. Let's check it. Minus dz by, yes. And then we have to take the curl of this one with the component of total magnetic field. So the two components of the wave in the transverse direction and the Z component, which is the constant externally applied magnetic field. So this is, let's write our Cramer rule, I, J, K. Then we have the first is dz by minus dz bx 0, and the second vector is bx by b naught. Okay, so we have the factor in front times. The first component is minus dz bx times b0 minus dz bx times b0. Then the second component is these, I wrote a dy, instead here is a by, magnetic field, okay? So let's do it again. So it's going to be dz by times b0, changing the sign, so minus dz by that multiplies b naught. And the third one is dz by minus dzx bx. So it's a cross term. dz by that multiplies by minus dz bx, and as a minus minus, so we change the sign 2 times, bx that multiplies bx. Okay, so let's put this together. Is there a signing? Okay, then where we were, we have this is the equation that we want to write. So we can express this as rho time derivative of the velocity field equals minus gradient of the pressure that is acting only on the Z component. Then we have plus J cross B dot. And if we now plug this result into our equation and we divide by rho both sides, so we divide by rho here, we got 1 over rho in front of this term and 1 over rho on the other side. Then we get to the following equation for the first two components. So we have that we can write, in black color, time derivative of the velocity field equals, we have B0 divided the rho, the mass density of the fluid, times mu naught, the permittivity, times the derivative of partial derivative along Z of the wave component of the magnetic field. So this means that this part of the equation is for X and Y. For X and Y components. Okay. The third component says that since we don't have time derivative of the velocity along the Z direction, 0 on the left, and what it remains is the gradient of pressure, which, if you remember, the gradient is only along the Z direction, so is dz of the pressure, minus the gradient of the magnetic pressure, PB, which comes from this term here. Let's see where it comes from. The Z component is equal to minus the, yes, is dz B squared half 1 over mu naught. So you can just apply the Z derivative to B squared, where B squared is the square of the wave solution, so it's By squared plus Bx squared. You get exactly this term here. So, and we can write it as minus what, if you remember, B squared over 2 mu 0 is the magnetic pressure of the fluid, is the magnetic pressure in MHD equation. Remembering that the gradient is only the Z component, so this is actually the gradient of the pressure. So we see that the two gradients have to be in opposite direction, and this is stating that that the gradient of pressure, no different color, okay, it means that we are in pressure balance, okay. It means that the gradient of the pressure of the fluid, so this is the thermal pressure, which corresponds to a force term, has to be in the opposite direction to the gradient of the pressure of the magnetic field pressure, so that the two gradients are balancing each other. Okay. And so we see that we are in pressure balance. This is the Z component. Okay, let's focus our attention on the two degrees of freedom, the transverse degrees of freedom, which are the wave components. And as we define this equation 1, we defined the second equation, equation 2, okay, which is exactly the same, has exactly the same structure of equation 1. Let's go back, see, where we had the time derivative of B and the spatial derivative dz of V. Here we have the same structure, time derivative of V with the spatial derivative of B. So exchanging the roles of B and V. Now we can combine the two equations into the wave equation for alpha n waves. So usually we take mixed derivatives. So we can go to from, this is a first order differential equation. We go to a second order differential equation. As you might remember that the wave equation is a second order partial derivative equation. So let's take on one side the time derivative of equation 1, and on the other side we take the z derivative of equation 2. So we want to find mixed term in the derivatives and cancel them. So what we get? Equation 1 time derivative on the left, we get the second time derivative of p equals to b0. Let's go and see what it was. And then we have the mixed derivative of the velocity field. So we have d, let's write it, dt dz of the V field. Then here what we do, we take the z derivative of this equation. So we have the mixed term in the velocity field. So we have dz of dt of the V field equals B naught is constant, rho is constant, mu naught is constant, and then we find the second spatial derivative along the z component of B field, taking the z derivative of equation 2. And now you see that we have this common term, and we can eliminate, cancel out this term. So we combine the two now. Okay, if we multiply on the left times B0, we have exactly the same term here. And on the right-hand side, we get B0 squared. So the square of the amplitude of the externally applied field. And then we can combine the second time derivative of B equals to this term. And this is the wave equation. So what we get is, in the end, the second time derivative of B minus, we take to the left-hand side the term, we have B0 squared divided rho divided mu 0 times the second derivative with respect to z of B of the magnetic field equal to 0. And this is actually the wave equation we were looking for. So this is Alfvén wave equation. So what does this remind you? So we have the second time derivative, we have the second space derivative, and what goes in front of the second space derivative is actually the speed of the wave. So this is exactly the same as the electromagnetic waves in vacuum or acoustic waves. So this term is the speed of the wave, which is called actually the Alfvén speed. So this is VA squared, which is P0 squared, the square root of the amplitude of the B field times rho times mu naught is the Alfvén speed. And we have a wave equation with a constant speed, which is the Alfvén speed. Constant, obviously, as long as the plasma conditions are constant. If not, obviously, you get a different Alfvén speed where the plasma has a different density or the external applied field amplitude is changing. So the medium, if it is uniform, is non-dispersive, and the plane solution are that we obtained are, let's say, now we can relax our description where we have just an externally constant field along the z direction. What actually it comes out is that if we put into ourselves into the frame of reference of the magnetic field lines, we get that, for instance, the field B field lines may be curved in this way. So this is the way the B field, external applied B field goes, and what it propagates along these lines are the magnetic field of the wave oscillating up and down in the transverse direction. So we have the B field of the wave, and at the same time we have the velocity fluid of the fluid, let's call it V, that are both oscillating normally perpendicular to the direction of the field lines. Okay, so this more or less is what is happening. The wave is propagating along the B field line, the external applied field. What is propagating is an oscillation in the B field that is convolved and in resonance, not in phase, not in resonance, with the fluid oscillation that is along is transverse to the field lines. What is the Alfvén speed? So pay attention that no linear approximation was used. So the intensity, the amplitude of these waves can be very, very large. So Alfvén waves are very important to consider, for instance, in magnetic confinement fusion, where we have a significant externally applied magnetic applied field. And in that case, Alfvén waves can transport quite a lot of energy and momentum from a part of the plasma to another one at very large speed. Let's see, for instance, what is the Alfvén speed. Are these fast or slow phenomena? Remember that somehow we neglected displacement current, so they are not, they are going to be slow phenomena, slow waves with respect to the electromagnetic waves. But they can be very fast compared to usual thermal waves and thermal motion and acoustic waves and so on. So they are much faster than the usual fluid dynamic of the plasma. So let's estimate for our purposes, so for our case study, what is the Alfvén speed? Our case study, remember, for external applied field will be the magnetic confinement fusion, MCF, which has a typical magnetic field of a few Tesla. In this case, to make it simple, let's use it, supposed to have a very large magnetic field, like 8 Tesla here. And we have the reference density is N particle per cubic centimeter is 10 to the 20 particles per cubic centimeter, per cubic meter, sorry. And let's suppose to have a fully ionized hydrogen plasma. So let's put it on the side to make some more room. Okay, here. And highlight these values. Okay. So let's compute, difficult to read. Better highlighted in yellow, okay. And so what is the corresponding Alfvén speed? So we have to take the square root of b squared. So on top we have 64 Tesla squared. Then at the denominator we have the density, bulk density of the fluid. So we have hydrogen plasma. So you might remember that the bulk of the density goes into the ion mass. So and the ion for hydrogen plasma is the mass of the proton, and the mass of the proton is something like 167 times. We go use a standard units, which is much simpler, minus 31. This is in kilogram. And okay, no, it's 27, sorry. Minus 31 is the mass of the electron. Then mass of the proton times the number of the protons per cubic meter, so 10 to the 20th. Then we have the for the vacuum permittivity, you know, that is defined as an exact number, is 4 pi times 10 to the minus 7. And we have to take the square root of this bracket. So we have, we can estimate, here we have 10 to the 20th at the denominator. We have 10 to the minus 27 makes 10 to the minus 7 times 10 to the minus 7 is 10 to the minus 14th. So we have 64 times 10 to the minus 14. And then we have the number at the denominator, which is 1.7, let's say, times 4 pi, and 4 pi is about 10, let's say. is 12 something. Okay. So this, let's check what it comes out, is let's do it properly. So we have 64 divided 1.7 divided 4 divided 3 is about 3. So we get 3 times 10 to the minus 14, and we have the square root of it. So the square root of 3 is 1.7 times 10 to the, actually, sorry, you didn't correct me, but this, since it was at the denominator, is 10 to the 14th. So we have 10 to the 7th here. What? International system, so is meter per second. And if you remember, the speed of light is 3 times 10 to the 7. So this is almost, let's say, 0.06 of c. So 6%, 5-6% of the speed of light. So actually, with respect to the usual acoustic speed, which are of the order of a few thousand kilometers per second or less, depending on the density of the material, you see that here we have a very large speed of this Alfvén wave. So the way of remembering this is, is, as I told you, the B field lines are like the strings of a violin, of a guitar, and the tension of these lines is very large. So the speed of the wave traveling along the field lines is proportional to the tension of the string. This tension is very, very high, and what you see is that the speed of this wave is a significant fraction of speed. It's not relativistic, but it's much, much faster than many other phenomena occurring at the fluid level. Okay, let's see the timer, where we are. So almost time to take a break. It's a nice moment to take the break. After the break, we'll see the parametric stability in plasma and the rocket. If you don't have any questions, we can take a break now. Or I'm here to answer your questions.
Salve professore, io le vorrei fare una domanda. Preferisce in inglese o in italiano?
Faccio in italiano.
Mi chiedevo se è possibile, attraverso la densità critica, creare una configurazione di plasma che riesca a confinare la radiazione di Bremsstrahlung. Però non riesco a capire di che frequenze si parli, perché lei ha detto appunto che dopo la densità critica la radiazione non si può più propagare attraverso il plasma. Ecco, si può fare questa cosa con la radiazione di perdita di Bremsstrahlung?
Le densità necessarie per la Bremsstrahlung sono troppo elevate in realtà. Quello che succede, il Bremsstrahlung
immaginavo.
le code negli X molli e anche negli X duri. Solo la parte più densa del plasma in confinamento inerziale riesce a intrappolare una parte della Bremsstrahlung. ma in generale diciamo, i raggi X molli attraversano la materia ordinaria senza grandi problemi. In ICF abbiamo compressioni dell'ordine di 100 volte o 1000 volte la densità solida normale. Ecco, quella parte lì è opaca per la Bremsstrahlung, ma tutta la parte esterna del plasma, dove il plasma è molto caldo, in realtà il raggio Bremsstrahlung ed è la perdita più significativa per tutte le forme di confinamento a cui noi pensiamo. Mentre la perdita per radiazione di ciclotrone è trascurabile rispetto alla Bremsstrahlung. In MCF la densità è talmente bassa che è completamente trasparente, quindi il problema non si pone. In ICF la configurazione è che quello che succede è che in confinamento inerziale, per come era, vediamo dopo, è assemblato il plasma, la parte esterna della corona è quella più calda che emette e emette verso l'esterno e tutta quella radiazione è persa. C'è una parte della Bremsstrahlung che viene riaccoppiata in maniera efficace con il nucleo, ma solo quindi con la parte più densa del bersaglio, ma solo verso la parte terminale dell'implosione, quando ormai non ci interessa più, perché in quel momento, quando partono le reazioni di fusione, le reazioni di fusione diventano dominanti e quindi nel bilancio energetico ormai il bilancio energetico salta. Bisogna fare le cose bene prima e prima in realtà il plasma è trasparente per la maggior parte dello spettro della Bremsstrahlung.
Ok, grazie mille.
Se ci sono condizioni di plasmi astrofisici in cui ovviamente uno può pensare di avere densità talmente alte nei nuclei delle stelle, nelle stelle di neutroni, nelle nane bianche, in cui effettivamente si raggiungono dei parametri in cui anche la Bremsstrahlung è intrappolata. Ma lì di solito il confinamento gravitazionale fa sì che anche la radiazione elettromagnetica, i fotoni sono intrappolati nel corpo celeste. Quindi sì, i plasmi hanno cioè, coprono in densità e temperatura uno dei campi più ampi della fenomenologia della fisica, perché vanno da molto rarefatti e freddi, praticamente prossimi allo zero assoluto, fino agli oggetti celesti più densi e più compatti, tipo le nane bianche, oppure le stelle di neutroni, oppure le quasar, oppure i buchi neri, in cui a un certo punto sì, la fisica diventa veramente complessa. Nel nostro corso l'infarinatura che dividiamo è quella di plasmi da laboratorio e per applicazione di fusione nucleare, quindi cercare di ottenere una fusione termonucleare controllata nel laboratorio per estrarne energia. Quindi questo è il framework in quale cerchiamo di muoverci e fare gli esempi. Ma la fenomenologia della fisica dei plasmi, come le ho detto, è talmente ricca e varia che è interessante anche per quello. Facciamo una pausetta e ci vediamo allora fra 5 minuti alle 9:05. Okay, here we are again for the last slot. Let's check the sound. Can you hear me? Mi sentite?
Sì, professore.
Ok, grazie. So the next topic is the parametric processes in plasma. So we have we're not going to deal this in very much detail. We are just going to present an application of all the different waves we have studied in plasma. If you remember, we have the longitudinal waves, the electrostatic waves, the ionic electrostatic wave. Then we have the transverse waves, so the electromagnetic waves in plasma. Then we study the acoustic waves, and then today we added the Alfvén wave. So at least 4 different waves that can be present in the plasma. And what are the parametric processes? Are describing the way different waves can interact with each other and excite resonantly themselves in according to phase matching of the wave solution. So we won't describe in our course the resonance processes. They are called usually parametric instabilities, because when we use, for instance, a laser that has a definite, very well definite, coherent in time and in space waves propagating inside the plasma. The laser acts as a pump that is constant in time for the constant oscillation frequency. So it is a pump that drives resonantly many different processes inside the plasma, which in turns can generate hot particles, hot electrons, super thermal particles, and so on. What we are going to show now is just the wave coupling. So how we can mix different kind of waves inside the plasma. So let's see. We don't study the instability, but we'll study the wave coupling only. So suppose that we have an incoming wave, which is described by an angular frequency, the incoming omega, and by a k vector, so a wave number k0. So this is representing the incoming wave. And then we'll see now that this wave can decay, can couple to different waves inside the plasma. So at a certain point, this wave can split in, for instance, what we call omega-1, another wave, which will have a k1 wave vector, and omega-2, k2 vector. So we we're going to use the particle description for the waves. You know that at the fundamental level, both elementary particles and wave can be described using the duality of particle and wave. So for instance, the electron can be described as a matter wave, using a de Broglie wave and so on, and can be done vice versa as well. So a wave can be represented by particles. You might have heard that, for instance, electromagnetic radiation is made of so-called wave packet that we call photons. So photons are a quantum of electromagnetic field propagating as a wave, and they behave, they have some behavior like that of a particle. So what we are going to use now is imagine that our waves are made of wave packet, discrete wave packet that we call, for instance, photons for the electromagnetic wave. So a particle or a quantum of wave will have an energy associated with the wave, which is h bar times delta omega. So the quantum energy associated with a wave packet, for instance, is h bar omega. And when we have an interplay with different waves, so we say that there's an exchange in energy between two waves when they change, when the angular frequency of the wave changes. And there will be an exchange in momentum as well. So what we call it delta P of the linear momentum, which at the level of a wave packet is expressed as h bar times the delta K. So this is the energy exchange of the wave, and this is representing the momentum exchange of the wave. So we, at the fundamental level, when we interact with different waves, we can apply the same arguments as we do with elementary particle. So in each wave interaction, we have to conserve energy, and we have to conserve momentum. So it means that we apply energy conservation. We require energy conservation in this phenomenon. So the incoming energy, represented by h bar omega, has to be equal to the final state energy. So it means h bar omega 1 plus h bar omega 2. I'm saying h bar by not writing it, because then we can simplify, obviously. And what it remains is just the relation of the angular frequency. This is expressing the energy conservation of the waves, and then we require momentum conservation as well. It means that delta P and delta E has to be 0 from the initial state and the final state of the interaction. So this means that let's project it in, okay, let's take the wave number. We have that k vector, initial k vector, has to be equal to the sum of the two k vectors after the interaction. And we'll divide our initial and final state. We call them incoming or reflected or transmitted wave, depending on the direction of propagation. Let's see what I mean. So for instance, let's take our one-dimensional dispersion relation. For instance, we put k, the wave number, and the omega. And for instance, let's suppose we have an initial state like this one here, which is represented by a point in the dispersion relation plot, and this is called the zero wave. We call it the incoming wave. So being on the right hand side, this is representing, for instance, a progressive wave that is incoming. and going this way. Then an interaction occurs, and what we can see, we have a transmitted wave in the same direction and a reflected wave in the backward direction. So we can pick up a point here, which is represented by the, for instance, a reflected wave. So let's suppose this is the wave number 1 in the final state, and is the reflective wave. And we have to satisfy the conservation of both energy and momentum. It means that we can work actually with the parallelogram rule. So we have that the final and initial state as vectors in this plot has to sum up to the initial state. So if we use the parallelogram rule, we can actually project this back here, and this is going to be the second wave, which is the transmitted wave. Which we give it a green color here, for instance, whatever it is. Okay. By using this parallelogram rule, we are sure that by summing 1 and 2, so we go to 2 and then we add up 1, then we satisfy that the sum of the two final states have the same omega, so the same energy of the incoming wave, and have the same k vector, the same momentum of the incoming wave. So that's the way we can couple waves together using this plot and using the vectors. So what are the dispersion relation we can mix? Let's suppose to have the three major relation that we discovered and studied. So let's draw this plot, which we are going to use quite a lot in the following. So I'll do once and then I'll copy it. So we have, let's use a color, for instance, red for the electromagnetic waves. So the dispersion relation for, let's put it omega and k here. For the electromagnetic wave, let's suppose we have here the plasma frequency. So the electromagnetic wave is a very steep parabola, kind of a parabolic here. Then we have the electronic waves, which go this way. And the final one is going to be blue, is the ion waves. Let's draw them like that. So let's give them the names. And first of all, let me copy it. So I'm going to use it as it is later on. Copy. Okay. So let's give them a name. The red curve is the electromagnetic wave. Electromagnetic waves. So the asymptotic speed is the speed of light. The minimum frequency is the plasma frequency. So here we have that this point here is represented by the plasma frequency for electrons. And we call these waves photons in our particle description. Then we have the electromagnetic, the electrostatic wave for electrons, so the longitudinal waves, and we call this the electron wave. And this electron wave is represented by a particle that we call plasmon. Okay, so it's represented by a wave packet that oscillate around the plasma frequency. That's why it's called plasmon. And the ion wave is much slower than the other two kinds of waves, as we might know, and we almost do not see the fact that is has the plasma ion plasma frequency here. So actually, what we see is that just the asymptotic part of the wave of the dispersion relation, where the ion wave has a constant speed wave. So is the part where the group velocity of the wave and the group phase velocity of the wave are the same. And we call these waves, in analogy to what it happens in matter usually, as phonons. So the phonons are quanta of acoustic waves. So usually associated with the motion of the bulk of the plasma, or of the lattice of a material, in this case with the motion of the ions. So we see that there are some characteristics. For instance, if we look at the ion waves, they are almost constant speed, if we look at them. So our approximation can see that this wave has constant speed. Instead, if we look at the plasmon, at electron waves, we see that they have a very high frequency, and they almost around the same frequency. So we can think of them as constant frequency. We put it in quotes because it's not constant, but it's slowly changing, constant frequency waves. So omega is of the order of omega plasma and is in this region. Instead, for the electromagnetic waves, both the speed and the frequency are changing quite a lot. So these are the three kinds of waves we are going to mix: photons, plasmons, and phonons. Okay, I forgot a plural here for the other two cases. Okay. So let's come to the first way of mixing these waves. So we're going to show see four of them, and let's see. I put a timer. I don't want to overshoot. Let's put it. Okay. So first of the four processes we are going to explore. So let's put it 1 out of 4. It's called parametric decay. You might know what in particle physics a decay means. Some particles and nucleus that decays into two fragments, for instance. So this is actually the idea of this workflow. So we have an incoming particle that decays into two final states. Here we have an incoming wave packet. So for instance, a photons that decays into a plasmon and another photon or whatever. So this is the way we want to use this relation and the conservation law that we stated here. Okay, so first of all, we have a parametric decay where our initial state is an incoming electromagnetic wave. That is decaying into an electron wave plus a ion wave. Using our description in terms of particles, we have a photon, an incoming photon that decays into two particles, a plasmon plus another particle, which is the phonon. Okay, let's see how it works. So let me paste back our plots here. And we have to start with a photon. So for instance, let's see. A photon means that the incoming state should be on this dispersion relation. And let's suppose the incoming is a progressive wave. So we have to find on this branch a point. And then we have to mix a point on a plasmon and on the photon on this dispersion line in order to match our incoming initial particle. So let's see how to do it. For instance, we could have I'll work backwards and then you see why. So we have this point here, and by using the parallelogram rule, I have to transport this plot here onto this curve. That's the way we reconstruct it. Okay, so these 3 points are linked and can represent such a process. Let's see how they are. So we have, oops, I pushed the wrong button, okay. So we have the incoming photon here. Whoa. Nope, I have to use this tool here. No, come on. Okay, so here we have the incoming. I'll use the black color so it's easier to see the relation, but it's not work. It doesn't want to work today. Too many lines. Okay, so we have the incoming photon. Then we have that goes here. Then we have the photon here, and if we transport this back from the incoming phonon, applying back this vector here, we hit the dispersion relation for plasmon here. So actually, our last point is this one here. So now we can have the incoming photon 0. We have a transmitted, so we can have a transmitted phonon here and a back reflected plasmon here too. show you why I'm using this description. So if this is incoming on the right, so it means that a photon is coming left to right, then who's moving still left to right in the same direction of the photon is the photon. So we have a transmitted photon, and instead we have a plasmon here, an electron wave that is propagating in the backward direction. So in this case, we have the incoming photon. We have a transmitted phonon, and we have a backscattered or reflected plasmon. Obviously, we can turn this the other way around. So we can have a reflected photon, and then we can couple a transmitted photon with a transmitted plasmon here. So usually the best way is to just get for instance, a line parallel to the phonon dispersion relation. So you take this one here, you copy, and from the incoming direction, you see that actually we can have this solution here, where we have a transmitted phonon, a reflected phonon, and the incoming photon, all three satisfying the energy conservation and momentum conservation. Okay, so you see that since this has a very little change in frequency, so that all these processes are occurring around the plasma frequency. Okay, we cannot have a very large plasma frequency, so frequency of the wave. Only when the wave is approaching the plasma frequency, then we can couple these three waves into this parametric decay. So it means that we have to require that the angular frequency of the wave has to be close to the plasma frequency of 4 electrons. And this, if you might remember, it means that the density of the electron has to be close to the critical density, which is where the plasma frequency is equal to the frequency of the wave. Remember that the critical density goes as omega squared of the incoming radiation. So these processes are occurring only around the critical density. So there are certain regions in the plasma where these parametric processes can occur into this in this way. So very close to where actually the light cannot propagate anymore, and has a frequency close to the plasma frequency, so that it can be coupled to a low frequency wave that is represented by the phonon. But this is an example. Let's try to understand better using a second example of the fourth. So let's go and see what is this, the second example is the two plasmon decay. So another decay, we call it the two plasmon decay. So as the the name of the process is self-explaining. So it means that we have a photon in the initial state, an incoming photon that decays into two plasmons. I guess I lost, yes, I lost in the clipboard the plot. So this is the one that I have to get back. Okay, I have to clean it a bit, but it's still the same plot. Okay, and let me clean it a bit. So take this out, this, that. Okay, so we are, okay, we can, now this is just annoying a bit. Okay, and let me make copy for later on. Actually, we are going to present 4 examples, so this is going to be the third one. And then we need the last one here. Okay, so this is ready. Two plasmon decay. So we have a situation where we need to find a photon here, and the way of coupling to plasma. You see that if we are too close to the plasma frequency, actually we cannot mix this one here with another photon plasma on this side, because the sum of the 2 omega will give something much higher. Actually, working back, you see, we have to sum up 2 plasmons that are more or less, they have to sit on the green curve. The sum of the 2 means that we need to have at least an omega of the laser, which is twice as the plasma frequency. And this will have actually a meaning. So let's take, for instance, a point here, which is represented by our incoming photon solution. And we have to find a way of picking up 2 points here that will allow us to do this trick. So more or less, let me check. For instance, let's pick up this point here. See if we are lucky. And copy. And we have to go back from that point, yes, more or less, to here. So actually, our good points are these 2 here. Pay attention the way I'm trying to find the solution by working with vectors using the parallelogram rule. Okay, so we have, for instance, that we have the 0 solution here, the incoming. Then let's use 1 for the transmitted. So we have a transmitted photon, plasmon, sorry, and a reflected plasma here. And the parallelogram rule is assuring that we have both energy and momentum conservation. So you see that actually, in this case, the omega of the laser has to be of the order and higher than twice the plasma frequency. Because as we said, the plasmon are almost constant frequency. So 2 plasmon are summing up to twice the plasma frequency. So we have to require the frequency of the laser of the photon has to be twice the value of the plasma frequency. So since we stated that the critical density is scaling as omega squared, then this means that this process can occur in a region of the plasma where the electron density is about a fourth of the critical density. So a quarter of critical density. This is a completely different region where this process can occur. So this is interesting to note that different parametric processes are occurring in different places of the plasma, because the plasma has, for instance, a density that changes from the outside, for instance, for the corona to the much denser part, the inner part. So it means that the plasma frequency changes from point to point, and depending on the local plasma density, different phenomena can occur. Imagine, for instance, a laser pulse that we are shooting from outside, and as it progresses towards the denser part of the plasma, it encounters higher and higher density, so higher and higher plasma frequency. So in turns, for instance, it will have a chance to go first in a region where it reaches the quarter of the critical density, and then this two plasmon decay can occur, and in this and if it can this photon can travel even more, can reach deeper in the plasma, and give rise to a plasmon, a parametric decay. Pay attention that if we our purpose is that of coupling energy to the plasma. What you see here, that we have the energy carried by the photon, which is represented by the omega. Remember that the energy associated with the quantum of a wave is h bar omega. So this is the energy that we want to couple, for instance, to the laser, to the plasma, and this is coming from the laser, for instance. And you see that this process splits this energy into two components. One that is an electromagnetic, let's look at this one here. One that is an electron plasma that travels in the same direction of the photon. So let's suppose that this is going towards the hotter and denser plasma, so still carrying the energy of the photons towards our target, our plasma. But this is a wave, an electron wave that moves away, so it's reflected back with respect to the incoming direction of the laser. So actually, and this is corresponds to energy of the incoming photon that is reflected back, so that the plasma is bouncing back towards us, and so it's not going to be absorbed. So basically will contribute to an energy loss if we want to couple our laser pulse to the plasma in order to hit it, for instance. So the analyzing these processes in terms of transmitted and reflected will allow us to understand what are the most critical phenomena that can actually reflect back most of the energy. That's what we don't want. So let's go to the third example. So 3 out of 4, and this is the a backscatter. Now we face two conditions of backscattering, and this is the Brillouin, is a French name, Brillouin. Scattering, you can say, pronounce it in the French way. Okay. And in terms of particles, it is described by an incoming photon. So we always, as before, we focus on for instance, a laser plasma and laser pulse that is hitting the plasma. So our radiation is a photon, that we want to couple to the plasma. So the incoming photon that decays into a phonon and another photon. So we have another photon in the process plus a phonon, so an ion wave. So for instance, what we do, let's suppose we have an incoming photon here. So this is our zero state, and we want to couple it with a phonon in the exit reaction. This is kind of a particle reaction. So in the final state, we have a phonon. So we know that this is the line that representing the phonon. So let's, as I did before, I want to find another photon. So another point sitting on the branch of the photon dispersion relation that can be connected by a phonon. So what I do, I take the phonon dispersion rule, I put it here, and I bring back this into and find an intersection on the refractive branch. So this is actually a good point. So and then using the vectors, I know that this is the reflected photon, and this is going to be the transmitted phonon 1. Okay, and obviously the incoming vector is this one here. So you see that is it quite dangerous for us? I mean, for who want to couple energy to the plasma using a laser. For instance, here you shoot a laser, a photon from the outside, and when you have the Brillouin scattering, what is happening is that you couple to the plasma a phonon here, which has little energy, small omega here, h bar omega, that it remains coupled to the energy, but most of the energy is given to a photon that goes back towards the incoming pulse. So actually, the plasma in this case behaves as a quite effective, almost ideal mirror. So it means that the difference in energy between the two incoming photon and backscatter photon is very small. So most of the energy is reflected back by the plasma, and just a little contribution is given to the plasma in terms of a photon. So this process is very dangerous. It's very detrimental for our purpose of heating a plasma, compressing a plasma urine, using an external source as an external source, a laser pulse. Okay, and so let's see, most of incoming photon energy is reflected back. So this is actually Brillouin backscattering, what we call it, backscattering. So we shine the laser, and that comes back towards us with very little energy deposition, almost as perfectly reflected by the plasma, if this is occurring. And as you can see, there's no particular region where this can occur, because if you if we take our I'm just doing this as a demonstration. If we take our dispersion relation, any point in the red curve and the dispersion relation of the photon, so can be easily connected with this line. Okay, so there are no particular limitation on the region or the frequency of the wave when this process can occur. Obviously, it cannot occur at a frequency higher, smaller than the plasma frequency below here, because there we don't have propagation of the electromagnetic wave. So here we are beyond the critical density, and the electromagnetic wave, the photon, cannot propagate anymore. So, but in all the region where the photon can propagate, you see, it's very easy to find a backscatter photon, and there are no limitation at all. Okay. Final. We are almost to the end. Yes. Final part is 4 out of 4, and is the Raman backscattering. So again, scattering, a photon in initial and final state. So we have a laser coming and reflected back. This is backscatter. And we have, in this case, instead of exchanging energy with an ion wave, is exchanging energy with the electron wave. So we have a photon in the incoming state that is reflected back. So we get another photon back, which is reflected, plus a plasmon which is transmitted. So in this case, it's a little bit more difficult to find the solution, because we don't have a straight line, but we can, for instance, take a point. We have to go a little bit higher, as we did before with the 2 plasmon decay. And let's suppose we need, let's start with the transmitted plasmon. It's easy to construct. The transmitted plasmon has to stay on this line here. So for instance, let's take this point. So this is going to be the transmitted plasmon. Then we have to take this vector here and trying to connect 2 points. Okay, they are sitting on the same curve. So one is going to be the incoming photon, and the other one is the reflected photon. In this case, we have solution 0 is the incoming photon. Then we have the transmitted plasmon, and okay, almost we have finished, and the reflected photon. So we see that, and this is solution 2. Okay, as you see, we need to be at least of the order omega has to be almost equal or higher than the plasma, twice the plasma frequency. So we have to be at least higher than quarter critical. And in this backscatter, we see that half of the energy, or actually a plasmon equal to h bar omega p, is given to the plasma, and then the other part of the photon energy, the incoming photon energy, is reflected back. If you go up higher, obviously you can still find a solution, and it will mean that just a small portion of the plasma, of the incoming energy of the laser, is given to the plasma, and a significant fraction is reflected. So this phenomenon is occurring at density higher than quarter critical, but and again is represented a way in which a significant fraction of the energy that we send to the plasma is coming back towards us in terms of a reflected photon, and only a fraction of the incoming energy is given to a wave that is inside the plasma. So this is what is the effective coupling to the plasma, is the energy carried towards the denser part of the plasma in terms of a plasma, so an electron. So we stop it here. We've seen quite a lot in about waves in these lectures. I'll leave the rocket equation and interaction with the solid target to Professor Azzeni, which will be a good introduction to a starting point for inertial confinement fusion next week. So I'm passing over to him for the last part of the course, which is dealing mostly with effective way of achieving confinement in the laboratory. So magnetic confinement fusion criterion and inertial confinement fusion, and different approaches for producing fusion energy in the laboratory. So I'll leave it here. And are there any questions?
Posso fare una domanda?
Sì, certo.
E io non ho capito, ma questi processi hanno associato una certa probabilità di accadere o accadono indistintamente? Cioè...
Allora, questi processi, quello che abbiamo visto sono le condizioni di phase matching o di wave coupling, quelle che soddisfano le condizioni di conservazione dell'energia e del momento. E questo ci permette di dire che questi processi possono occorrere se soddisfano a questi requisiti. Poi quello che succede è che il meccanismo può innescare una instabilità parametrica, ovvero questi processi possono avvenire in maniera risonante con le condizioni di plasma e quindi effettivamente diventare importanti e assorbire una significativa quantità di energia dal laser, oppure riflettere una significativa quantità di energia. Avvengono in modi diversi in diverse zone del plasma. Comunque questo è quello che non abbiamo visto, ma che aggiunge un grado di complessità in più, è che abbiamo fatto la conservazione dell'energia nel momento in una dimensione. Questi grafici che abbiamo fatto sono per k vettore d'onda in una sola dimensione. Se guardate le equazioni che ho scritto all'inizio, in realtà vedendo questi come particelle, vedete che la conservazione del momento viene fatta in 3 dimensioni, quindi anche l'aspetto del fotone e del plasmone o del fonone generati devono essere affrontati con la loro direzione spaziale, quindi c'è un aspetto in più. Lo scopo di questa parte è vedere che le varie onde che abbiamo studiato non solo esistono e il plasma le può generare e le può sostenere, ma che le stesse onde fra di loro si parlano, quindi fotoni, fononi e plasmoni, cioè generano in diverse zone del plasma. Quello che succede è che un'onda, in quanto tale, si muove da dove è prodotta e attraversa il mezzo, quindi il plasma. Quindi porta la sua energia e il suo momento in una certa regione del plasma dove le condizioni per le quali sono state prodotte cambiano e può essa stessa dar luogo ad altre onde o mescolarsi con altre forme d'onda. Quindi questi sono è un'infarinatura di quello che può avvenire nel plasma e la complessità del fenomeno delle onde che si mescola con i fenomeni di dinamica fluida. Ovviamente su scale un po' diverse, e di volta in volta le condizioni di plasma ci permettono di studiare e valutare quale di questi fenomeni è importante ai fini della dinamica di plasma oppure delle diagnostiche. Noi possiamo mandare radiazione elettromagnetica per, ad esempio, scaldare il plasma e quindi avere un risultato dal punto di vista di accoppiamento energetico col plasma, quindi vogliamo vedere dei risultati sulla dinamica del plasma dal punto di vista del fluido, oppure possiamo mandare della radiazione elettromagnetica per scopi diagnostici, in cui vogliamo vedere, ad esempio, il backscattering Raman e Brillouin possono essere usati anche per determinare, ad esempio, dove sta la densità critica o dove stanno il quarto della densità critica, osservando la radiazione riflessa e vedendo dove viene riflessa. Quindi questi processi permettono anche di, siccome alcuni avvengono in determinate posizioni nel plasma per quanto riguarda la densità elettronica, di mandare un segnale come diagnostica e guardandone la riflessione dove avviene e in quale direzione avviene, stimare la posizione dinamicamente, quindi ad esempio un monitor online delle condizioni di plasma che ci permette di dire la posizione ad esempio della densità critica. Che quindi avendo varie diagnostiche, ad esempio gli spettri che raccogliamo con la Bremsstrahlung e con la radiazione di ciclotrone ci dicono qualcosa sulla temperatura e mandando queste cioè usando questi processi potremmo sapere qualcosa sulla distribuzione di densità. Combinando le due, quando abbiamo la distribuzione spaziale di temperatura e densità, abbiamo una buona descrizione delle condizioni di plasma.
Grazie mille.
Va buono. Rimanete connessi. Vediamo qua.